for this problem, we're asked to compute the moment, MO, of the 250 pound force about the axis, OO. So for this one, we might consider this like the positive direction for rotation around the axis, so that if our moment is headed this way, it's the negative direction. All right, let's begin by sort of writing the components here for this force, and I want to sketch those components. So let's grab our force arrows. So we'll have one component here, and then one component back here, and then another component straight up. And if you can see here, let me maybe put on some axes, just so a person has some bearing. We might call this an x-axis, and back here we might call a y, so that this is a z direction. Let's put a squiggle. So this is fx, and then we have our fy, and then our fz. And fx is equal, well, it would be 250, and then the cosine of 60 would drop the force down into the xy plane, and then times the cosine of 40 degrees would move it over to the x-axis. That would be 95.8 pound. And then Fy would be 250 times the cosine of 60, and then times the sine of 40 degrees, which would give us 80.3 pounds. And then our z component would be 250 times the sine of 60, and that would give us 217 pounds. So those are the force components. Okay, now it's helpful to kind of do this problem in a scalar approach. We don't need to use vectors for it. The components and the distances are easy enough to spot. So note that the way OO has been drawn, it's really parallel to the x-axis. So Fx is not going to contribute to any moment around the O-axis. But MO would be equal the way that we have it. So Fy will make a moment. It might help to sketch a couple of lines over from where our force is applied to the axis so that you can see the distances. If we were to maybe sketch this line, is going to pass under and would come out maybe somewhere right in here, so that it's going to be, if we extend this O-axis through here, it would be below it by an amount that's equal. Well, from the very bottom, note that up to axis O, it's 8 inches, but then from the very bottom up to the y component, it's 4.2 inches. So this is really 8 minus 4.2. And as our Fy component travels along this line of action, it really goes underneath of this O-axis. And so it's going to create a moment that really goes around the axis in a positive direction by the right-hand rule. And so we're going to have, let's just do this as a scalar, we're going to have 8 minus 4.2 times Fy. Let's put that component back where we got it. And then if we think about Fz, his distance is easy to see, it's 12 inches. And as he goes past the O-axis, he is also going to create a moment that has this tendency to go around so that it gives us a positive directed moment. So this will be plus 12 times Fz. So this is equal to 8 minus 4.2 times 80.3 plus 12 times 217. And MO is equal to 2,900 pound-inch. Again, the components are easy to spot, and their moment arms are easy to spot. So there's no need for us to do anything more for this problem. All right. So that's the end of that.